Hey guys, now I will explain the first question. This question is, let P be a production function given by P equals 0.54 L squared minus 0.02 L cubed plus 1.89 K squared minus 0.09 K cubed, where L and K are the amount of labor and capital respectively, and P is the quantity of output produced. And we need to find the value of L and K that maximize the P. So the first step, we need to find the critical point. So we let the first derivative of function P with respect to L equal 0. And then find the derivative. We can get the answer is 1.08 L minus 0.06 L squared equals 0. And the answer of L is equal 0 and 18. Next, we also need to find the first derivative of the function P with respect to K equals 0. And the derivative is 3.78k minus 0.27k squared. And the answer of the k is 0 and 14. So the critical point are 0, 0, 0, 14, 18, 0, and 18, 14. Next, we need to base on the theorem 5 to classify the critical points. If the d is greater 0 and the second derivative function of f is greater 0, so the function f is a local minimum. If the d greater 0 and the second derivative function of f with respect to the x is less than 0, then the function f is a local maximum. If the d less than 0, then the function f is not a local maximum or minimum. The point is called center point. And if d is equal 0, then the test is inconclusive. First, we need to find the second derivative of the function p with respect to L is equal 1.08 minus 0.12 L. And then we need to find the second derivative function p with respect to k equal 3.78 minus 0.54 k. After that, we also need to find the first derivative of the function p with respect to L and K is 0. After that, we need to construct a table to substitute each critical point into the second derivative function P with respect to L and with respect to K. And also, we need to substitute into the first derivative function with respect to L and K and the function D. On the critical point 0, 0, we can know that the function d is greater 0. And the second derivative function p with respect to L is also greater 0. So we can know that the critical point 0, 0 is minimum. And the next critical point 0, 14, and also 18, 0, both critical point on function d is less than 0. So the point is settled. And the last critical point, 18 and 14, on the function d is greater 0. And on the second derivative function with respect to the L is less than 0. So the point is maximum. We need to choose the maximum point, substitute into the function p, so we can get 182 units of output produced. We can conclude that 80 labor and 14 capital maximize P, where the maximal output produced is 182 units. Guys, have any problem?
Sorry, can I ask where did you get 1.08 L minus 0.06 L squared per 0?
Okay, we get the equation of the first derivative with respect to the L is from the function P. So we need to see the variable L. So we 2 times 0.54, so we can get 1.08. And we need to minus 1 from power 2, so we get the 1. After that, for this, we need to times 0.02 times 3, and then we can get the answer is 0.06. And also need to minus 1 from the power 3, so we can get the power 2. After that, the behind the equation is not variable L. So we get 0.
Oh,
Clear?
okay. Okay, yes, clear. Thank you.
Okay.
Uh, and then the question is for the table.
For the table.
How do you know that the for table 2 and 3, how do you know that the number is negative or positive?
Alright, we need to substitute each critical point in the function on the second derivative function. Like we substitute 0, the first is L and K. So we substitute this function. So L is 0, so we substitute the 0. So we can get the first is 1.08. The next also we substitute the critical point into the function, so we can get 1.08. Next also substitute 18 into this function, so we can get negative 1.08. And the last critical point also we substitute the point of the L is 18, so we can also get negative 1.08. So after the next equation also the same, we need to also substitute the critical point into the function, each function, so we can get the answer.
Okay.
Okay, now I will explain about the example 51, which is the question. They suppose P, which is a production function of a firm. So they want us to find the quantities of input of L and K so as to the maximize output of P. So they already give us the production function P, which is this one. And for the first step, we need to find the critical point. To find the critical point, first we need to do a derivative of input L and also input K separately and make equation to equal to 0. First, we use to input L equal to 0. This is the first derivative of input L, and we get the L has a 2 point, which is L at 0 and also at L at 24. For the input K, we use the derivative of from these equations. So we get the second we get the derivative of K equal to 0, and we get K has a 2 point, which is K equal to 0 and K equal to 14. So we get a 4 critical point from this equation, which is a 0, 0, 0, 14, 24, 0, and 24, 14. Okay, then second step is we need to classify the critical points. So this is the equation that state from the theorem 5. So first we need to find the second derivative of input L and also second derivative of input A, and the first derivative of input L and K equal to 0. So when we for the critical point, for the first one, we get when we enter the point 0, 0 into the equation of a second derivative of L, which is this one. So we get 2.16, which is more than 0. So when we enter the equation, this equation into the equation of D, we get 7.2576, which is also more than 0. So from the definition of A, if a D is more than 0, which is this one is more than 0, and fxx AB is more than 0, which is input L more than 0. So the f function is a local minimum. Therefore, when for this critical point 0, there is a local minimum. For the second and third one, when we enter this critical point into the L function and also K functions, we get this value. So when we enter this critical point into the D functions, we get that the D is less than 0. So from the definition of C, if D is less than 0, so the F function is not local maximum or local minimum. It's called a saddle. So for critical point 0, 14 and 24, 0 is a saddle. For the last one, critical point 24, 14, we get this value when we enter the critical point into the equations. So and the D is more than 0. So from the equation of B, if D is more than 0, then fx, which is this one, is less than 0, then function f is a local maximum. So we enter the because the question want the maximum, right? So we enter the critical point of 2414 into the function of P. The first, this is the equation of the questions. So we enter the critical point 24, L for L 24 and K 14 into the equation, and we get of the units 3, 170.12. So we approximate to 317 unit of the outputs. So therefore we get when input L is 24 and input K is 14, enter into the production of to maximize the P. To maximize the P, we need to use the critical point of 24 and 14. Okay, that's all. Any question?
Sorry, Atika.
Yeah.
May I ask you, where did you get 2.16 L, 2.16 L and minus 0.09 L square equals 0? Is it same as example 50?
This one, right?
Yeah.
Yes, it's example from example 15 that Sergi already explained, but I will explain to you again. This because in order to find the critical point, we need to find the first derivative of input L and also input K. So this is the first derivative of input L and this first derivative of input K. So 2 times 1.08, we get 2.16. So for the derivative, we need to times the power and after that minus the power. So after we time and we need to minus the power. Same goes with 0.03 times with 3 and the power of L is 2 because 3 minus 1.
Okay, thank you. Now I understand.
Okay.
Okay, let's see another applications of the partial derivative in the production functions. Example 52. The production functions for a firm is FLK equals to 12L plus 20K minus L power to 2 minus 2K power to 2. The cost to the firm of L's and K is 4 and 8 per unit, respectively, if the firm wants the total cost of input to be 88. Find the greatest output possible subject to these budget constraints. From the question, we know that this is our production functions, and now we have our budget constraint. This question is different from the previous question as this time we have the constraints. The constraint is 4L plus 8K minus 88 as you can see that L and K is 8 and 8 per unit and should be equals to 88. For these questions, we will use the methods of Lalang multipliers by forming new functions f, x, y, and lambda. Since in these questions, our variable is L and K, so we substitute x and y with L and K respectively. So this is our first new functions, and our FLK lambda equals to production functions plus lambda multiplied with the constraint functions. Please take note that our constraint should equals to 0. So get our new function. Then we have to find the critical point for these functions by finding FL, FK, and F lambda. So to find FLs, we differentiate these functions by treating the variables k and lambda as a constant. So we differentiate and we get our FL is equals to 12 minus 2L plus 4 lambda and equal it to 0. And it's same as to find the Fk equal to 0 and F lambda equals to 0. We differentiate these equations but with respect to variables k and lambda respectively. And now we have 3 equations. So we need to find the L value, K value, and the lambda. We look at this. Here we get 4 lambda, and here we have 8 lambda. So the easiest way is to eliminate the lambda by taking the second equations, we divide by 2, and now we can see that here become 4 lambda. So we take the first equations to minus the fourth equations, and now we get a new equation that is k equals to L minus 2, 1. So we substitute k equals to L minus 1 into the third equations, and we get that L equals to 8. And we substitute L equals to 8 into the fifth equations, and we get that k equal to 7. And since we get L equal to 8 and k equal to 7, and we can simplify the lambda values by substitute the values into equations 1 or equations 2. And in here, I use the equations 1. So we get that lambda will be equals to 1. Now we know that the critical point is 8 and 7. And we can know that this is a local maximum point by simply see this equation, as this will tend to negative infinity if the L and K increases. So this point will be the local maximum. So we substitute 8 and 7 into the production function, we get that 74 units of the output will be the greatest output. So in conclusion, subject to the budget constraints, 8 units of L and 7 units of K will produce the greatest output, that is 74 units of output. Is it any questions?
I have one question. Can I use
Yes.
the second derivative test to determine whether the point is local minimum or maximum if I don't know how to see directly from the function?
Yes, sure, you can use. You can just use the second derivative test for these equations or these equations, since that our critical point is the critical point for this when the lambda is 8 is equals to 1. For just for your knowledge, for your understanding, and this question, we only have one critical point, so we have to classify the point through this method. But if there are more than one, the points, you can just directly see from the value by substitute the critical point to the production function and take the greatest value that will be your local maximum. Is it clear?
Yes, thank you.
All right. Since this is the last questions, so that's it for our discussions for today. Thank you all.